2 miles down, in total darkness, water is supposed to move the way it has moved for millions of years. Slow, predictable. A conveyor belt so steady that oceanographers built entire climate models on the assumption that it barely changes at all. It isn't behaving that way anymore. Off the coast of Mozambique, scientists dropped dozens of instruments onto the seafloor expecting to confirm a current flowing quietly north to south, the way textbooks said it should. What they got back instead left them, in their own words, gobsmacked. In the North Atlantic, a 2,000-mile system of rotating currents that has driven Europe's climate for 10,000 years is showing signs so unusual that researchers are now openly using the words tipping point. And in the Southern Ocean, a patch of surface water is doing something it has never done in the era of satellite observation, refusing to warm while the rest of the planet cooks around it. None of this is science fiction. It's happening right now, and as of today, August 14th, 2026, scientists still don't have a complete explanation for it. This isn't a story about a single discovery or a single research paper. It's about 3 separate teams of oceanographers working in 3 different parts of the world using 3 completely different methods, whose findings, taken together, paint an unusual picture within the space of about 2 years. Several major ocean current systems appear to be behaving in ways existing models didn't predict. To be upfront about something important, these 3 stories are not confirmed to share a single common cause. Scientists have not established a proven link tying the Mozambique reversals, the Atlantic slowdown, and the Southern Ocean anomaly into one unified mechanism. What connects them, for now, is timing and a shared theme, not a demonstrated shared cause. We'll come back to that distinction because it matters. To understand how unusual each piece is on its own, we first need to understand just how confident science used to be about the way this system worked. For most of the 20th century, oceanographers treated the deep sea the way early mapmakers treated the far side of the world. A flat, mostly featureless void, worth noting, but not worth worrying about. The real weather, the real climate engine, was assumed to live up top. Winds, surface currents, the top few hundred meters where sunlight still reaches. Below that, the story went, water crept along in slow, steady, essentially unchanging rivers, insulated from the chaos above by sheer depth and pressure. That assumption wasn't lazy. It was based on genuinely limited data. Deep sea monitoring is expensive, technically brutal, and until recently, sparse. A handful of instruments scattered across an ocean covering 70% of the planet was enough to sketch a rough picture, and that rough picture got copied into textbook after textbook, model after model for decades. The problem is that a rough picture built on sparse data has a way of collapsing the moment you actually go looking closely. And over just the last 2 years, 3 separate lines of investigation, one off the African coast, one across the North Atlantic, one in the Southern Ocean, have all gone looking closely at the same time, and all come back with the same unsettling message. The deep ocean is not the quiet, predictable place we assumed it was. It's worth remembering, too, that even the basic existence of vigorous deep currents was a hard sell in oceanography for a long time. Early researchers, working mostly from surface observations and the occasional dredge sample, pictured the deep sea as close to still, a calm, dark basement beneath a restless, wind-driven surface. It took decades of advances in bottom photography, sediment sampling, and eventually moored current-measuring instruments to prove that the deep ocean has its own weather, complete with storms, eddies, and fast-moving jets of water capable of scouring the seafloor. In other words, the field has already had to overturn its own assumptions once before. What's happening now might be the second time. Start with Mozambique, because it's the case that most directly rewrites the textbook. A team of researchers, led by scientists from the UK's National Oceanography Centre, anchored 34 acoustic Doppler, current profilers to the seafloor off the Mozambique coast, instruments designed to track the speed and direction of deep water movement over an extended period, rather than a single snapshot. The expectation, based on decades of prior modeling, was simple: a steady current flowing from south to north, moving at a fairly constant pace, the kind of predictable conveyor belt behavior that global ocean circulation models are built around. That is not what the instruments recorded. Instead, the data showed currents reversing direction, speeding up and slowing down on timescales far shorter than anyone expected, and generally behaving with a level of chaos that the lead researchers described as far more dynamic than anything in the existing models. One senior scientist on the project put it bluntly: these conveyor belts of currents that circle the entire planet are going to be far more complicated than the textbook models suggest, and they warrant serious, careful investigation. Why does this matter beyond one stretch of seafloor near Mozambique? Because those same textbook models aren't just academic diagrams. They're the tools scientists use to track how pollutants and microplastics disperse across the ocean floor, how sediment moves and buries carbon over geological time, and how ancient climate conditions can be reconstructed from the seafloor record. If the underlying assumption that these currents are steady and predictable turns out to be wrong in one well-studied region, researchers now have to ask an uncomfortable question: how? Many other deep current models, built on the same sparse historical data, are quietly wrong in the same way. There's a technical wrinkle here that makes the Mozambique findings even more striking. The instruments used, acoustic Doppler current profilers, work by bouncing sound waves off tiny particles suspended in the water and measuring how the frequency of that reflected sound shifts, the same Doppler principle behind a police radar gun. To calculate speed and direction with a precision earlier generations of researchers simply didn't have access to. Deploying 36 of them simultaneously, rather than the single mooring or occasional shipboard measurement that used to pass for deep current monitoring, gave this team something genuinely new: a dense, continuous, multi-point picture of how water actually moves along a stretch of seafloor over time, rather than a handful of scattered snapshots, stitched together with assumptions filling the gaps. It's a bit like the difference between judging a city's traffic patterns from a single dashcam clip versus a live citywide network of cameras. And once researchers finally had the citywide network, the traffic turned out to be far messier than the dashcam ever suggested. The proposed thermal burp mechanism deserves a closer look because it illustrates just how counterintuitive deep ocean physics can be. But it's worth being blunt about its status. This is a hypothesis floated by some researchers, not a confirmed finding, and it hasn't been demonstrated to be happening. The Southern Ocean is unusually good at absorbing heat and pulling it downward, away from the surface, into deeper layers where it's effectively hidden from the atmosphere and, historically, from most of our instruments. Some researchers hypothesize that decades of accumulated heat sequestered this way in Antarctic deep waters could eventually resurface, not gradually, but in a comparatively abrupt pulse, driven by changes in the density layering that currently keeps that heat locked below the surface. If that mechanism turns out to be correct, it would mean the ocean has effectively been buying time on a portion of global warming by hiding heat out of sight, and that the bill for that borrowed time could come due on a timeline measured in years or decades rather than centuries. Again, this remains an unconfirmed hypothesis, one of several competing explanations, not an established outcome. But it's exactly the kind of hypothesis that keeps oceanographers pushing for more consistent, higher resolution monitoring of what's really happening beneath the southern ocean's surface. Nature documentaries love to frame moments like this as unprecedented, and often they genuinely are, within the window of modern instrumentation. But paleoclimatology, the study of ancient climate using evidence like ice cores, sediment layers, and yes, clamshells, tells us the deep ocean has shifted dramatically long before humans were around to measure it directly. The most famous example is a period scientists call the Younger Dryas, roughly 12,900 years ago, when a sudden dramatic slowdown in North Atlantic circulation plunged the northern hemisphere back into near glacial conditions in what geologically counts as the blink of an eye, likely triggered by a massive pulse of glacial meltwater disrupting the same sinking process that drives AMOC today. That event unfolded over centuries, not decades, and the meltwater source was catastrophically larger than anything happening now. It isn't a direct preview of what's coming, but it is hard proof, written into the geological record, that this exact system has undergone abrupt, dramatic reorganization before, triggered by a mechanism, freshwater disrupting deep water formation, that closely resembles what many scientists suspect is happening today, just at a different scale and speed. That historical precedent is part of why researchers take today's warning signs seriously, rather than dismissing them as short-term noise. Here's a detail that rarely makes it into the headlines, but matters enormously for understanding why this mystery has taken so long to even notice. For most of history, we simply haven't had the tools to watch the deep ocean continuously. Surface currents can be tracked from space relatively easily. Satellites can watch temperatures, patterns, color, and texture shift across the sea surface in near real time. The deep ocean offers no such shortcut. Historically, understanding what's happening a mile or more down has required physically dropping instruments into the water and waiting, sometimes for years, to retrieve them and see what they recorded. That's an enormously slow, expensive way to build a global picture of a system that covers most of the planet. That's finally starting to change, at least at the surface. In April 2026, a team led by researchers at UC San Diego's Scripps Institution of Oceanography and UCLA published a new AI-driven method in the journal Nature Geoscience, nicknamed GoFlow, Geostationary Ocean Flow. It's worth being precise about what it actually does. GoFlow uses machine learning to analyze thermal imagery from weather satellites already in orbit, detecting how surface temperature patterns shift over time to reveal small, fast-moving surface and near-surface currents, eddies and boundary flows as fine as a few kilometers across, that older satellite methods blurred into meaningless averages. The team validated it against real ship measurements in the Gulf Stream and found strong agreement with far greater fine-scale detail than existing tools provided. It's a genuine advance, and it's part of why ocean current research generally is having something of a moment right now, but it's important not to overstate it. GoFlow maps surface and near-surface flows, not the deep seafloor currents at the center of the Mozambique findings, and it hasn't been used to directly resolve the AMOC or Southern Ocean questions discussed above. Its relevance to this story is more indirect, a sign of how quickly ocean observation technology is improving overall at exactly the moment several separate anomalies are being reported. That's a crucial and somewhat humbling point to sit with. Regardless of which specific tool is doing the observing, some portion of what looks like the ocean suddenly changing might actually be us gaining new abilities to observe variability that was already there, hidden beneath the resolution limits of our older instruments, separating genuine, novel. Change from newly revealed pre-existing complexity is one of the hardest and most important jobs facing oceanographers right now. Consider how thin our historical baseline actually is. Continuous, high-quality monitoring of AMOC strength through a dedicated observation array only began in the mid-2000s. Before that, scientists were largely reconstructing the current's past behavior indirectly through methods like the clamshell chemistry mentioned earlier, or through sparse historical ship measurements that were never designed to capture the kind of fine-grained, moment-to-moment variability modern instruments can detect. That means when researchers say a current is behaving in a way unprecedented in the observational record, it's worth asking, honestly, how long that record actually is. 2 decades of dense, direct monitoring data is enough to detect a real trend, but it's a thin sliver compared to the centuries or millennia over which these systems naturally cycle, which is exactly why scientists keep reaching for indirect archives like sediment cores and shell chemistry to extend the picture further back in time. It would be easy to file all of this under interesting but distant. Currents moving strangely a mile beneath the surface, thousands of miles from land. The reality is the opposite. These systems are directly wired into the climate everyone on the surface actually experiences. If AMOC continues to weaken significantly, the consequences reach far beyond a slightly colder Western Europe. Models associated with a serious slowdown point to disrupted rainfall patterns across the tropics, patterns that hundreds of millions of people depend on for agriculture, along with accelerated sea level rise concentrated specifically along the U.S. East Coast because of how the current's weakening changes water distribution across the Atlantic basin. Separately, researchers have connected the Atlantic's cold blob to measurable shifts in the Indian summer monsoon, a seasonal weather system that more than 1 billion people rely on for their water supply and their harvests. A current reversing off the coast of Mozambique might sound like a narrow technical detail, but the sediment and pollutant transport models, built on old assumptions about that current, directly inform how coastal nations plan for erosion, contamination, and fisheries management. In other words, deep ocean currents are not a sealed-off curiosity. They are one of the load-bearing walls of the entire planetary climate system, largely invisible, rarely discussed, and, as of this year, visibly cracking in ways researchers are still racing to fully map. Fisheries offer another concrete example of how directly these systems touch daily life. Deep currents carry oxygen and nutrients along the seafloor, effectively fertilizing the food webs that surface fisheries ultimately depend on. Off Mozambique specifically, researchers have noted that the newly discovered variability in seafloor currents could reshape how nutrients are distributed along that stretch of coast, with knock-on effects for local fishing communities that current management plans, built on the old steady flow assumption, were never designed to anticipate. Multiply that single regional example across every coastline where deep currents interact with continental shelves, and the scale of what's potentially at stake becomes much clearer. This isn't an abstract climate statistic. It's the machinery underneath a huge share of the world's seafood supply. Shipping and infrastructure planning quietly depend on this same machinery too. Submarine cables that carry the vast majority of the world's internet traffic are routed, in part, based on assumptions about seafloor stability and current behavior in the regions they cross, offshore wind and wave. Energy projects, increasingly common as countries build out renewable infrastructure, factor deep in near-bottom current data into engineering decisions about anchor points and structural loads. None of these industries are designed around the expectation that the currents beneath them might reverse or intensify on short notice. A scientific correction to how predictable these systems really are doesn't stay confined to academic journals. Eventually, it works its way into engineering codes, insurance models, and infrastructure budgets that most people never think about until something built on the old assumptions fails. It's worth being precise about where the real uncertainty sits, because that's ultimately the honest heart of this story. Scientists are confident that deep ocean currents are more variable on shorter timescales than the models used for decades assumed. The Mozambique data makes that hard to dispute. They're confident that a specific, well-monitored current system in the North Atlantic is weakening based on multiple independent lines of evidence, spanning direct temperature readings and centuries of clamshell climate records. They're confident that the Southern Ocean is diverging from model predictions in a way that isn't yet fully explained. What they don't know, and what genuinely constitutes science can't explain it yet, rather than clickbait exaggeration, is the underlying mechanism tying these regional stories together, if one even exists. Is this a single planet-wide response to accelerating climate change, showing up differently in different ocean basins? Is it multiple unrelated regional phenomena that happen to be surfacing in the same handful of years, partly because we finally have better tools to detect them? Or is some of it simply the deep ocean revealing a level of natural background complexity that was always there and that our historical models were too sparse to ever capture? Right now, credible researchers are actively arguing all three positions, sometimes about the very same data set. That disagreement isn't a failure of science. It's what science looks like in the middle of a genuine unresolved puzzle, before enough evidence has accumulated to settle it one way or another. This is also where funding and infrastructure decisions stop being a side issue and become central to the story itself. Resolving a genuine scientific disagreement requires more data, collected consistently, over enough time to distinguish a real trend from short-term noise. The planned removal of hundreds of deep-sea monitoring instruments in the Atlantic, instruments that were specifically deployed to track the AMOC weakening currently at the center of this debate, doesn't just slow down the search for an answer. It risks permanently erasing the ability to answer the question at all by leaving a gap in the data record at precisely the moment researchers most need it to be continuous. Oceanographers who've spoken out against the decision have framed it in stark terms. You don't diagnose a patient's declining heart rate by removing the monitor.